Hi! In the last video, we've learned how to calculate determinants. We learned how to calculate determinants for matrices with dimensions 1 by 1, 2 by 2, and 3 by 3. We also said that there is no easy rule similar to the ones we've learned for bigger matrices. So look, if we will have matrices 4 by 4, 5 by 5, and so forth, the only way to calculate determinants for those matrices is to resort to a technique called Laplace Expansion. Now, what is the idea behind this technique? Well, the idea is that using Laplace expansion, we can rewrite bigger determinant into a series of smaller determinants in a very specific way. But okay, before we can use this technique, I need to teach you two new concepts. First is going to be called minor. Minor is a subdeterminant of A obtained by deleting if row and j column. Okay, let me give you a simple example. So if we have determinant A11, A12, A13, A21, A32, A12, A13, A22, A23, A32, A33. Right? So now I want to calculate minor. So if I want to find minor 1, 1, what do I need to do? Look, it tells me that I need to delete ith row and jth column. So in this case, all I need to do is to delete first row and first column. And what I get left is minor 1, 1. Now, if I want to find minor 3, 2, what do I need to do? Now, I need to delete third row, second column, right? So, what am I getting is A11, A21, A13, A23. Okay, so as you see, it's not complicated. All we need to remember is we obtain minor by deleting row indicated by the first number and column indicated by the second number. And then the second concept we need to introduce is called cofactor. And cofactor is a minor with assigned algebraic sign. Okay, what does it mean? It means that in order to get cofactor, first we need to find a minor and we need to add either plus or minus in front. How do we know whether should we add plus or minus? This is really simple because we can write this down easily in the form of the formula -1 to the power I plus j. And the rest is simply minor 1, 1. So look, all I need to do is to put -1 and take it to the power indicated by the sum of the location of the element for which we calculate the cofactor. Okay, So basically we can get here only minus or plus if the sum of the two is a negative one, if the sum of the two is odd, or 1 if the sum is even. Okay, so let's check it for our previous case. So cofactor C11 is simply negative 1 to the power 1 plus 1 times n11. So this is just 1. So it is the same as our minor. Then, if I want to find cofactor C32, I'm taking negative 1 to the power 3 plus 2 and multiplying by the minor 32. Here, because we were taking to even power. So we got 1. Here we are taking to odd power, we get negative 1. So we obtain that this is negative A11, A13. A21, A23. Okay, and with all of this, we are ready to actually perform Laplace expansion. Okay, so I'm gonna, of course, to keep things simple, I'm gonna explain how to do Laplace expansion on the example of a determinant 3 by 3. So, how do we do it? Look, the entire idea of Laplace expansion is that we can choose any row or any column and perform expansion in along the lines of a very specific procedure. Okay, so because we can choose any, let me first just choose the first row. So, we are always expanding by the entire row. So, I'm starting with element A11, and then I need to multiply this element by cofactor C11. Then I need to add element A12 multiplied by cofactor C12. And then I need to add element A13 and multiply by cofactor C13. Okay? So now let me just calculate. Okay, so I get that this is A11 times negative 1 to power 1 plus 1 times the cofactor, times the minor. And the minor, if I do it first row, first column, right? Because this element lies in the first row, first column, so cofactor for this element will be everything left if I delete those two. Okay, and this is A22, A23, A32, A33. Okay, then I need to add to it A12 times negative 1 to the power 1 plus 2 times the cofactor. So I delete now first row, second column, I get A21, A31, A23, A33. Okay. Finally, I need to deal with the last expression, and now the cofactor is given by negative 1 to the power 1 plus 3, and times the cofactor. So what we've got left, if I delete this, right? So I get A21, A31, A21, A31, A22, A33. 2. Okay, now, look. We are doing it very slowly now because this is our first time. But look, even now we can see that this will be just 1, right? So I can get rid of this. We see that this is going to be negative 1. I can get rid of this and just put negative a1, 2 in front. And here, this will be just 1. So I can get rid of this all the way. And now look. The only thing left is to calculate everything out. Okay, so look, here we calculate regular determinants, 2 by 2, which is very easy. All we need to remember is we need to multiply each component by an element up front and take into consideration the size. So we get that this is A, 1, 1, A, 2, 2, A, 3, 3. Minus now A, 1, 1, A, 3, 2, A, 2, 3. Right? Because here we are going downstairs. When we are going downstairs, we keep the sign. Here we add minus up front. Okay, and then we need to repeat the same thing for all the expressions. So now we will have negative A1, 2, A2, 1, A3, 3 plus A1, 2, A3, 1, A2, 3. And then we will have plus A1, 2. I'm sorry, A1, 3, A2, 1, A3, 2. And then minus A1, 3, A3, 1, A2, 2. Okay, and if we multiply this all out, we will get the value of the determinant. And, but I also said that it is irrelevant which row or which column are we going to choose. If this is so, this means that if I, for example, say the first column, and I'm going to expand by this entire column, I should get the same result. So let's check it. Okay, so if I'm now doing expansion by the first column, my first element will be A11 times negative 1 to the power 1 plus 1 times A22, A32, A23, A33. Right? Because I need to have element times negative 1, 1 plus 1. Because this is the location of this element, and then I add the minor. Okay, then I'm adding another expression. This time I'm going to A21 negative to the power negative 1, 2 plus 1, and now I calculate the minor here. So in order to calculate this minor, now I need to delete second row, first column. And what I get left is what I should put in as my minor. Then, finally, I need to add the last element, so A31 times negative 1 to the power 3 plus 1. And now if I delete third row, first column, this is what I have left. A12, A13, A22, A23. Okay, now let's get rid of the expressions with negative 1. Here we will have just 1. Here we will have just 1. Here we will have negative 1. Right? So I need to just put minus up front. Okay, so now again I need to calculate this using exactly the same procedure as we did before. Okay. A11, A22, A33 minus A12, A32, A23. And okay, then over here, then we will have 2, 1, A3, 2, A1, 3. And finally, out of this, we're going to have plus A3, 1, A1, 2, A2, 3, and minus A3, 1, A2, 2, A1, 3. Okay, assuming that I didn't make any simple mistake, we should have it. Okay, let's compare the two expressions. Well, we clearly see that we have the same element over here and over here. Okay, so this element also appears here. Here, also A11, A32, A23. This is exactly what we've got here with the same sign. So checks out. And look, it makes perfect sense that those will be identical because this expression is the same as this expression we had over here because those are associated with the same first element. Okay, but let's look at the rest. Okay, what else do we have here? Here we have the minus A21, A12, A33. Okay, the same as the expression over here. Then, what else do we have? We have plus A21, A32, A13, the same as here. And what then? We've got plus A31, A12, A23, the same as this. And finally, we've got A31, A22, A13. Checks out. So, look, I know this is not a formal proof, but the formal proof for the case of the determinant n by n is a little bit beyond the scope of this class, so we are not going to consider it. But I hope that this simple exercise is showing you that what we are getting here by expansion by any row or any column, on the example, of course, of these two, is the same expression at the end. But you can say, okay, maybe those expressions are identical, but can we check if what we are getting out of it is a determinant? Well, we can do it in exactly the same way. We can just calculate it, right? Using the procedure we learned last time. So we would have A11, A22, A33. Okay, let me just erase those blue tapes because we will have to use them again. Okay, then I would have A12, A23, A31, A12, A23, A31, and then A13, A21, A32. A13, A21, A32. Now we will be subtracting, so we go in the opposite direction. We've got A31, A22, A13. Then we've got minus A32, A23, A11. This, and this. And finally, A33, A21, A12. Okay, and again, let's see if the results we are getting are actually matching. So, well, clearly those two are identical. No problem here. Okay, so let's start maybe with positive. Yeah, then we've got A12, A23, A31. We've got this one in both. And A13, H1, A32, the same. Okay, now let's move to negative. A11, A32, A23, A11, A23, A32. Those are the same. Okay, then we see here that we've got negative A12, A21, A33. And we got it here. And finally, you can see that also those two expressions expressions are identical. Okay, so look, what have we learned thus far? We've learned that actually using Laplace expansion in the following way, we can calculate the determinant by making a series of smaller determinants, right? We learned, because of course those two are giving us the same result. And we also learned that it doesn't really matter which row or which column we are choosing, because we always get the same result. And look, all of what we said is going to be pretty useful when we calculate determinant with actual numbers. Why is that so? Look, if I'm actually calculating a determinant, and I can choose any row or any column, I probably should choose the one that has the most zeros and ones, because this is going to be the one that is going to be easiest to calculate. Okay, but before we go into examples, we need to figure out a formal definition of Laplace expansion. How do we do it? Okay, and look, again, this is something that definitely can be written down using some symbol. Okay, and now, what I want to do over here is to write this entire row using some symbol. Okay, what will I definitely have in my sum symbol? At most, I can have 3 elements, right? Definitely. Now, I need to have a's and cofactors in my expression, right? And now let's see what is changing and what is not changing. We see here I have 1, 1, 1, 1, and I have 1, 2, 1, 2, 1, 3, 1, 3. So look, I should use ones over here. And then what is changing? What is changing is the number of the column we are using, right? So what do we see over here is the formula for expansion by the first row, right? Now, if I want to do the same thing, but for example, I want to now write down the expansion by the first column. How should I do it? Well, again, at most I can have 3 elements. I will have A elements and cofactors over here. But look, my first element would be A11, C11, then A21, C21, A31, C31, right? So, what is changing now? Now we are changing the location in the column, but we are changing the location through rows. So now we would have I1, I1, I equals 1. And this one we could call expansion by the first column. Okay, and I know this is very tricky at the beginning, but remember, when we do expansion by the first row, we are actually moving along the columns. This is why the column index here is changing, well, when we do expansion by a column, we move through rows. So this is why the first index is changing. But look, this is not a formal definition. What if I would have determinant a 1, 1 until a n 1, a 1 n until a n n? What should we do in such circumstances? Look, as it turns out, even from these formulas, we can use them, modify them slightly, and we will get a full-blown definition of how to add elements in Laplace expansion. First, what do we need to change? We need to change 3 to n, right? Because now we have n elements. And look, if I want to make a Laplace expansion of this determinant with respect to first row, by expansion by the first row, this definition is now correct, and by the first column, this definition is now correct, right? But what if I want to include the fact that I can do it by any row or any column? Look, here we need to change just one thing. Here I would introduce I, and this would be the expansion by each row, right? We just need to now substitute I with the row we want to choose. And if I here change 1 to j, I will have expansion by j column. Okay, so now we have formally seen how Laplace expansion works. So the only thing we've got left is to learn how to do it, how to use it. And well, the best idea for that is to do some examples. And remember, Laplace expansion, just like matrix multiplication and generally determinant, is not something you learn by heart. You just need to practice. If you calculate 10 or 15 different determinants using Laplace expansion, I can guarantee you will know how to do it for the rest of your life. Okay, so let's start. Let's have an example. We need to have something. Okay, so let's just say that now we've got 5, 2, 7, 6, 3, -3, and 1, all. Okay, look, because we are doing this for the first time, we are going to rewrite this. We're not going to write this step by step, but of course in the future, I'm just going to make it faster. Okay, look, this determinant, we know how to calculate the normal. But let's start with the smaller one, then we will move to bigger and bigger determinants a little bit later. Okay, so definitely, remember, if I can choose any row or any column for the expansion, I should choose the one that is the easiest, so the one that has the most zeros. And look, in this case, the clear choice would be the third column. Okay, so now we are doing the expansion by the third column. So, first element is 1 times -1, and we take it to the power, this lies in the first row, third column, 1 plus 3, and I multiply it by a minor, 2, 3, 7, -3. Okay, then plus. Okay, and look, in the future, this is where we can stop, right? Every other element of this expansion is 0, so this is all we have. But just to practice, at the beginning, today we're going to got that this is 0 times negative 1 to the power, right? Second row, third column, and times what we have left if we delete second row, third column, so 5, 6, 7, negative 3. Okay, and then plus, we have, again, we have 0, now times negative 1 to the power, third row, third column, and times the minor, 5, 6 to 3. Okay, now we clearly see that we don't need this and this expression because those are just 0. And we don't need this as well, right? Because 1 plus 3 is 4, so we get just 1. All we need to do here is to calculate 2 times negative 3, which is negative 6 minus 2, 7 times 3, which is 21. So we get that this is negative 27. Okay, but of course, look, if we have a situation like this, we don't need to use Laplace expansion. Although, look how faster you could do it if we use just this instead of using it in a regular way. But of course, we need Laplace expansion mostly for the more complicated cases. Okay, so now let's go into into this slightly more complicated case. So we now have determinant 4 by 4. Remember, if you have determinant 4 by 4, there's no way you can do it, you can calculate it in any other way, just Laplace expansion. No formulas like those we used before. Okay. Again, I should start by finding either a row or a column. In this case, I think the choice is clear. What we should choose is the column number 3. And look, this time I'm not going to get into such details. Look, this part of the expansion, this part of the expansion, and this part of the expansion will be all equal to 0. So all I need to write here is just 4 times negative 1 to the power, second row, third column, and times the minor. And because there is only one element, I'm going to do this. By doing this, it will be easier to rewrite everything. 1, 2, 9, 1, 6, negative 1, 0, negative 5, 8. Okay, and look. This is simply negative 4 times negative 1. So this is what we've got. Okay, but because we are learning Laplace expansion, we're going to deal with this case also by Laplace expansion. So I put negative 4, I open brackets, and what will we have inside? Okay, again we should choose a row or a column. Well, in this case, the easiest column, I believe, would be this one. We've got 0 and 2 1s. Definitely not a very problematic number. Okay, so I start here. 1 times negative 1 to the power 1 plus 1. And times the minor, 6, negative 1, negative 5, 8. Then the second element, so we've got plus 1 times negative 1 to the power 2 plus 1, and times the minor 2, 9, negative 5, 8. Okay, now we clearly see that this is just going to be 1, and this is just going to be negative 1. Right, so basically, at this moment we can calculate everything step by step. Over here I will have 6 times 8, which is 48, and minus 2 times 16, which is, I'm sorry, 2 times 8, which is 16. So negative 16 and plus 45. Out of this, but we've got minus in front, minus 45. Okay, so how much do we get over here? Out of those two, we get 3, we get negative 2, 3, 3, negative 2, negative 18, negative 18 times, negative 18 times 4 should give us 72. Okay, so now that we've dealt with 3 by 3, 4 by 4, well, this is definitely a tie for determinant of the size 5 by 5. Okay, and look, this is the type of the exercise you can expect on your final exam. And what is important, remember, I always provide an easy way to get out of the determinant, which of course, give me a second, 0, which of course is the road you should take if you want to do it quickly and without many problems with complicated calculations. Okay, 1, 3, 6, 2, 7. Okay, and now again we start by Laplace expansion. We're going to do Laplace expansion. We start by choosing the best row or a column. Here, definitely, this is the column we should use. Okay, and so what am I writing? 1 times negative 1 to the power 3 plus 3 times the minor. So I get that this is 3, 8, 1, 2, 0, 1, 0, 0. 0, negative 1, 1, 0, 1, 3, 2, 7. Okay, and we clearly see that this is going to be equal to 1, so I can skip this. Not sure. Okay, then, again, I need to choose a row or a column. Now, clearly, this is going to be the best column because it has the most zeros and just 1. So, I get that this is 1 times negative 1 to the power 2, second column, 2 plus 2. And now, if I delete everything here, what I have left is 3, 1, 2, 0, 1, 0, 1, 2, 7. Again, we see that this is equal to 1. So now, let's use Laplace expansion one more time. We clearly see again that this is the best choice. So, what am I getting out of this is 1 times negative 1 to the power 2 plus 2 times 3, 1, 2, 7. And again, I see that this is equal to 1. 3 times 7, 21, minus 2 is just 19. Okay, so this is how we use Laplace expansion. In the next video, I will be discussing some properties of determinants that will actually make all the calculations of determinants even easier than those that you've seen over here. Okay, thank you for your attention and see you in the next video.